Hello, this is Mr. Stein, and in this video we are going to go through the example problems to illustrate the properties of functions. After these videos, you should be able to define and give examples of functions, identify functions in different representations, change two-variable equations into a function and vice versa, use function notation to determine values of a function, and use set notation to list the domain and range of a function. All right, we're going to take a look at the example problems. Example number 1. For each relation below, A, determine whether the relation is a function. Functions are one-to-one or many-to-one. Justify your answer. Identify the domain and range of each relation that is a function. Right. Letter I. A relation that associates a number with a prime factor of that number. This relation is in set notation. Notation of ordered pairs. We can see that 4 goes to 2. 6 goes to 2, 6 also goes to 3, 8 goes to 2, 9 goes to 3. Okay, immediately we can see that this is not a one-to-one function. If it was a one-to-one function, there would be every item in the domain would be unique, and every item in the range would also be unique. But you can see neither of those are the case here. This is not a one-to-one function. Is it many-to-one? Well, 4 goes to 2. Also 6 goes to 2, so that is many-to-one. 8 goes to 2. There's 3 items going to 2, 3 domain items going to 1 range item. 6 goes to 3 and 9 goes to 3. So yes, it is many-to-one. But is it also one-to-many? Well, let's take a look. We have one domain value, 6, going to many range values. If we have a domain value that goes to 2 different range values, it is not a function. This is a one-to-many and a many-to-one graph. We call it a many-to-many function. Anytime you see a domain value more than once in an ordered pair representation, it will not be a function. It will be a function if you see every domain value exactly once. So this one is not a function because the domain value of 6 goes to more than one range value. A relation is not a function if it has a domain value that goes to more than one range value. Let's take a look at the second one. Our domain value January only goes to one number. That's good. Our domain value February only goes to one number. That's good. Our domain value of March only goes to one number. That's good. Our domain value of April only goes to one number. That's good. This is a one-to-many relation. And a one-to-many relation is a function because each value in the domain goes to exactly one value in the range. So now we're going to write the domain and the range. the domain. The domain is the set of all values that are January, February, March, and April. That is our set of domain values. Our range values are 28, 30, and 31. You can see that for a function, the domain values do not have to match up the number of range values. You can have more domain values than range values. You cannot have more range values than domain values. And this is a one-to-many function. This is a one-to-many relation, therefore it is a function. Each item in the domain goes to exactly one item in the range. Example 2. The range shows the cost of student bus tickets, C, dollars, for different numbers of tickets. So you buy one ticket, it's $1.75. You buy two tickets, it's $3.50. Three tickets, it's $5.25. Four tickets, it's $7. Five tickets, it's $8.75. Why is this relation also a function? Well, let's take a look. Does every item in the domain go to exactly one item in the range? Our 1 goes to 175, our 2 goes to 350, our 3 goes to 525, our 4 goes to 7, our 5 goes to 875. Every item in the domain goes to exactly one item in the range. So yes, A, it is a function. Each item in the domain goes to exactly one item in the range. Letter B, identify the independent variable and the dependent variable. Well, the independent variable is always the domain. So this one's independent. And our cost is dependent. Now, if you think about it, and if I say it like this, the cost depends on the number of tickets bought. That makes the most sense to you. The cost depends on the number of tickets bought. That makes the cost the dependent variable, the number of tickets the independent variable. If I said the number of tickets depends on the cost, well, it kind of works, but it doesn't really work that well. Because when you're going to the bus station, you say, I want 4 tickets. And the cost depends on the number of tickets you buy. So, but in math, our range value is always our dependent variable, and our domain value is always our independent variable. Now, we're going to write the domain and range. Letter C, the domain. Now, according to this graph, strictly, our domain is 1, 2, 3, 4, and 5. But it makes sense that you could buy more tickets, right? But you can't buy, well, you could even buy 0 tickets, couldn't you? That would give you a cost of 0. No, not really. Because it doesn't exist. It's not the same. But you could buy 6 or 7 tickets. You could not buy decimal numbers of tickets. You can't buy negative numbers of tickets. You can't buy fractions of tickets. We could say our domain is the variable n such that n can be any, well, we could do whole numbers. 0, 1, 2, 3, 4, 5. Or we could say that n is any natural number. 1, 2, 3, 4, 5. This is a better way to write the domain. Our range, well, strictly according to that table, it's 1.75, 3.50, 5.25, 7.00, 8.75, but it could be lots of other numbers. It depends on the formula, the relation between these two. But because it could be more numbers, we can do something similar to what we've done with the domain here. So we could say that our range is our variable c, such that c could be some number, not in the natural numbers because we have decimals, not in the whole numbers. We could say that c could be any rational number. It could be part of the rational numbers. Because it has to be a terminating decimal. It has to terminate after 2 decimal place values. So our range is our value c, such that c could be some rational number. And what that rational number is depends on the number of tickets sold. Or sorry, the number of tickets bought. Okay, so this is identifying the domain and range and writing the domain and range in set value. Now I'm having problems again with this app, so I'm going to quickly relaunch it. Let's take a look at example 3. The equation c equals 25n plus 1,000 represents the cost, c, in dollars, for a feast following an Arctic sports competition, where n is the number of people attending. So we have a relation in 2 variables. C dollars, the cost, n is the number of people attending. Describe the relation. All right, so describe the function, Write the equation in function notation. So let's describe this function. This is going to be a linear function. C is the cost in total in dollars. N is the number of people. Then 25 is the cost per person. Every time a new person comes, we have to add on $25. So this is the cost per person, or the rate. And the 1,000 is the fixed cost. If nobody shows up, if we get 0 people, we still have to pay $1,000 because we have to give the caterer $1,000 to start buying food and everything. So they have a fixed cost of $1,000, and then every person that comes is going to get an extra $25 charged. Now we're going to write this equation in function notation. So the cost of our banquet, given how many people show up, is equal to 25 times the number of people plus $1,000 for the fixed cost. This is now in function notation. You should be able to take a 2-variable equation and turn it into function notation. Letter B. Determine the value of C of 100. 100. This is the number of people. So we're going to determine the cost if 100 people show up. So our cost for 100 people, actually I'm going to just step back. Because it's not on the page, I'm going to write out my function. C of n is equal to 25n plus 1,000. So C of 100 is equal to 25 times 100 plus 1,000. It's equal to 2,500 plus 1,000 is equal to 3,500. So what does this number represent? So C of 100 equals $3,500 means the total cost will be $3,500 for 100 people. All right, now let's take a look at letter C. To determine the value of n when C of n is equal to 5,000, what does this number represent? So now we know our total cost, and we're asked to find the number of people. That would give us that total cost. So I'm going to write down my function. C of n is equal to 25n plus 1,000. Now, since C of n is equal to 5,000, C of n is equal to 5,000, I replace C of n with 5,000. Now I work the formula. I subtract 1,000 from both sides, and I get 4,000 is equal to 25n. Now I divide both sides by 25, and I'm going to get n is equal to I can't do this one in my head. 160 people. So we get this. The cost of 160 people is equal to $5,000. So for $5,000, we can have 160 people at the banquet. All right, let's take a look at what are the domain and range of the function. The domain. Now, when we look at our function up here, this is always our domain variable. That's our domain variable. Our range variable is that one out there. So our domain is the number of people. So our domain, it's the number of people such that, well, we could have 0 people. We could have 1 person. What happens if 0 people show up? Well, you have $1,000 to spend on nobody. N could be any whole number. That will be our domain. Now our range value is all the C's, all the cost, such that cost is going to be an element of the wholes as well. We're not going to get any decimal values. So that is going to be our domain and our range values.